Hello students, and welcome to this video here where we are going to go ahead and talk about how to do all the problems on the ionization worksheet. In general, this entire thing is to get you ready for any type of question you can have with ionization energy. You'll get the most out of this video if you are watching through specifically for any questions that you are having issues with, listening to the explanation and then trying to solve them on pausing the video and then solving them on your own. However, I will be giving the answers to these questions as we go along. So the very first question is essentially having us use a graph, and in particular it's having us use this graph right here. And it's wanting us to go ahead and list the ionization energies just for each of these four noble gases. Okay. And so we can look at the gases here, and the very first one is helium, and it looks like that's right about like 2350. So we would want to go ahead and put helium, probably a dash, and then we're going to go ahead and put 2350. Our next one looks to be neon, and it as you can take a look here, we have neon, and it's also at the top of its column. So we're going to go ahead and put neon, and that one looks like it's about 2100. Now the exact amount isn't going to be too important because again, this worksheet is all about finding the trends that are going on. Next, we can go ahead and look for argon, and as we trace through our elements here, we see argon, and argon looks like it's about right under 1600. So I'm going to put like something like 1560. All right, just because it looks like it's right under 1600. And then I noticed something. I noticed that I myself do not have the next two on here. However, since I already see this trend that it looks like all of these elements are slowly going down and they're also at the top of their level, I can probably make a good prediction here. And I should be able to predict that, hey, our next one would probably be about right here on the graph, and that's probably going to be about 1200 or so. And that would be krypton. So just by taking a look at the first three, I can probably predict about where the next two are going to be. And I'm going to say that xenon's probably going to be about 1000. Okay, and I'm basing this based off of our three previous numbers here. Okay. Number two, it's asking us to go ahead and make a statement about the trend in observed energies as we go down a group. Okay, and in this case, we should notice that, hey, we went helium, neon, argon, krypton, xenon. They're all in the same column. All of them are increasing in their atomic number, but they're also increasing their energy level. So we can go ahead and say that we noticed a trend where ionization energy decreases occurs when we go down a group. And this relates really well to our idea of those energy levels, that as we go down, this is essentially 1s, this is 2p, and then each energy level, the atom gets bigger, and because it's bigger, it can't hold on to those electrons quite as well. So that's what's going on with these ones here. So we would write that ionization energy decreases when we go down a group, due to an increase in the energy level. And that would be all that we really need to go ahead and indicate here, that we have an increase in our energy level from the periodic table, and we have a decrease in our ionization energy. Okay, now number three is another one where it's just wanting us to go ahead and look at these graphs and say, hey, where is our ionization energy? Okay, and lithium here, it looks like it splits the difference. I'm going to say that's about 600. Then we're going to look at beryllium. And beryllium looks like it's about 900. Then we have boron, and notice that boron goes down just a little bit, so boron's about 800. We have carbon next. Carbon's a little bit higher. Let's say that's about 1100. Nitrogen's a little higher over that, maybe 1300. Oxygen, that dips down again, that's about 1200. Fluorine, this is about 1700 here. Okay, fluorine's quite high. And then finally our neon is the very top, and we had that at 2100 last time, so we're going to put that at 2100 this time. All right, and so that's all number 3 is asking. It's wanting to make sure that we can read that graph and understand what, how to graph those numbers. Question 4 is asking what's the general trend in ionization as you move across the second period. Okay, and we'll take a look at our periodic table. This right here, this row right here, this is our second period, and we can see that from lithium to neon, in general, as we go across here and our numbers increase, we should see that there's a general trend for it to increase. And this is just asking for the general trend. So our general trend for the second period is that the ionization energy, and we're going to label it as IE, increases. And that's all we have to do for number 4. Okay. Next, we're going to have to go ahead and draw an example of the neon and sodium ions using our Bohr models. Now, we went over this really quickly. But the idea is that we want to go ahead and look at each of our elements here. And we're going to start with neon here. And neon is going to have a total of 10 electrons. Okay. And we can use our periodic table to help us figure out the first row, the first energy level, it has 2. Okay, 1, 2. And this is similar to our 1s. Okay. Now, our second energy level has both 2s, 1, 2, and it has the 6p. So we're going to go ahead and have 1, 2, 3, 4, 5, 6, 7, 8. Okay, and this is what we have for neon. Now we go ahead and look at it, sodium, and sodium we can see right here, it has 11 electrons. And so it's going to start off the same way, where it's going to have 2 in that first energy level. So 1, 2. It's going to have 8 in that second energy level. And now I realize that I should probably change my color for the electrons. So 1, 2, 3, 4, 5, 6, 7, 8. And right now we have a total of 10. But we need to have one more, so we're going to have to draw another energy level on the outside. And we'll draw this last electron right here. Okay, and this is what we would need to have essentially for our answer. Okay, this is going to be much easier to draw on hand than with a mouse, by the way. Okay. Next, number 6, it's asking us to go ahead and use our models to explain why the first ionization for sodium is so much lower than neon. So let's go ahead and take a look at this. And it looks like neon's up here, and its first ionization energy, that the energy to take that first electron, is so much higher than sodium's, which is way down here. So that's what it's wanting us to explain. It's wanting us to explain why do we have this difference, and it wants us to use this image right here. And how we can do that is we can say, all right, well, it looks like the pull for those protons to get the electron is more for sodium, because sodium's going to have to go through 2 levels there. And that's an example of what we called electron shielding. Okay, so the fact that sodium has to go through 2 different energy levels to hold on to this outer level is an example of electron shielding. And then the other thing that's going to affect it is the fact that sodium's going to be a little bit larger. And it's going to be a little bit larger, more so because this outer level also has to go around those 2 inner levels. And because it's so much larger, it's going to be easier for us to take that newest electron from it. So that's what we want to put in our answer here. That because of the extra energy level, the electron is easier to pull away from sodium due to it having a larger size and being further from the nucleus, and also having electron shielding from the previous second energy level. Okay, and both those factors are kind of keeping that electron, making it easy for us to go ahead and steal that away. Now, number 7 is saying that there's a spike in ionization energy for nitrogen, phosphorus, and arsenic. What do all of these ionization energies have in common? Okay. So right here, it's saying that, hey, there's a spike right here for nitrogen. There's also a spike right here for phosphorus. And we can go ahead and imagine that there's also a spike for arsenic. And it wants us to go ahead and explain why there is a spike for this. And it's giving a hint that we want to go ahead and think about our orbital diagrams. Okay, so let's go ahead and take a look at where all of these sit. And I want you guys to take a note that, hey, nitrogen, phosphorus, and arsenic all sit in the 3rd of their p orbital. Okay, so they're all in the 3rd of their p orbital. Since they're all in the 3rd of their p orbital, that means that all of them are going to have a diagram that's going to end very similar to this, where they're going to have 3 up arrows, okay? So this is going to be what nitrogen ends with. This is going to be what phosphorus ends with. And finally, arsenic's going to end up ending with a 4p, and it's going to have the exact same thing going on. Now, earlier when we did electron configuration, we learned that in general, the more parallel spins you have, the more stable an atom is. And in this case, we have 3 orbitals with 3 parallel spins. And so we want to go ahead and put that they still have the same number of orbitals and the same number of parallel spins. And that they've maximized those number of spins. So we would put that all these elements end in P and have 3 electrons with parallel spins. And have 3 electrons which maximize their parallel spins. And that would be all that we need to go ahead and have to satisfy this type of question. So this is just a good callback to what we were doing before with electron configuration. Next, for number 8, it wants us to go ahead and draw a orbital diagram for nitrogen and oxygen. Now, luckily here, they already have it here drawn for us. It's a little hard for me to do that one, so we're going to go ahead and make a new one right here. And we just recently did nitrogen, how it ended, and we have to do oxygen. Okay. Now, nitrogen has a total of 7 electrons. Oxygen has 8. Our first box is 1s. Our second box is going to be 2s. And our final box would be 3s, which actually ends up being 3. And nitrogen and oxygen, they both start the same way. You know, they have those 1s orbitals filled. They have those 2s orbitals filled. And then they fill up all their p orbitals with 1. And then oxygen has 1 extra one. So if you counted, you'd see that we have 7 right here for nitrogen. And we have 8 here for oxygen. Now, because this extra one is here, it kind of has a little bit of repulsion. Okay? But I think this question, the first question, is just to draw it out here. Okay, so that's all that 8 is. So just drawing out our electron configuration would satisfy it. Looking back here, it's saying to use this diagram now to explain why it's easier to remove this outer one from oxygen. Okay? And we'd be able to say, just by looking at this, like, hey, these ones are all alone, so they have no other electron to try and push them away. Whereas this one here has an extra electron, and it's trying to push that one electron away. So that's why we would go ahead and put, for our answer here, that electron repulsion happens on the last electron that enters the p orbital, or that enters a half-filled p orbital, because it has one already in there, making it easier to remove. Okay. And then finally, on this front page, the last one that we have, it's asking us to explain why we have these big drops for lithium, sodium, and potassium. And this is something that we kind of went with before and explained that, hey, every single time that we have an element, so for instance, He, it's going to have its energy level, and it's usually going to be fairly tight. And it's going to have those electrons in there. And those electrons are really as close as they can get, okay? And then when we go ahead and go up an energy level, okay, so once we've filled up our 1s orbital, we're now going to have to go ahead and put in a new energy level. So lithium, its first energy level, is about the same size as helium. Okay, we're going to put pink for electrons for lithium here, because it does have a nice pink color when you light it. Our next energy level, though, has to be much bigger than this, okay? And the reason that it has to be bigger is simply because it has to go on the outside. All right? So it's bigger because it's on the outside. Okay? And so it has a much further distance from the nucleus, and the nucleus has to travel through this level. Remember, every energy level between the nucleus and the energy level where our last electron is kind of acts as a shield. So this is another case where we'll go ahead and say that as we go up energy levels, the size increases and the electrons are further away from the nucleus, making them easier to pull off, and they are shielded by the previous energy level. Okay, and that's what we'd do for every single time we kind of go up an energy level, is we'd want to explain that both of those factors are going on right there. All right. Now, we're going to go ahead and move on to the second page, which is 11. Okay, and 11 again is asking for factors affecting ionization energy. Okay, use the appropriate factors. Okay. And essentially, it's asking what's going on with our general line right here, okay? And the first thing that we have to go ahead and say is that in general, effective nuclear charge for all of these is always increasing, okay? Our periodic table, we're always adding more protons as we go along. So in this particular case, for this problem, we would have to indicate here that this one is increasing, okay? Now, overall, we would then look at our shielding and say that in general, our shielding is increasing for each new level, but then staying constant through each energy level. Our shielding is increasing in general for each level. Okay, and then we can also go ahead and put kind of in a lower highlight that it's a little bit constant as well. And so we want to explain that, in general, shielding increases by each level that we go up. But stays constant in each subshell. Okay, so whenever we start a subshell, That means that we're going to go ahead and have our shielding stay the same. Okay. So whenever we start the P subshell, that means that we go ahead and have a new bit of shielding, and that shielding continues on until we reach the next energy level. Next, number 3 is atomic radius. And what we should say is that there is something that is going on with atomic radius, that in general, as we are going down the table, atomic radius increases, but as we go from left to right, atomic radius decreases. Okay, so in this particular one, we would go ahead and put both of these. We're going to go ahead and highlight both. Okay, we're going to say that atomic radius increases as we go down the table, but decreases as we move from the left side of the table to the right side of the table. Okay. Number 12, considering the first 4 ionization energies for an element we'll call A. Now this one's going to be very similar to some free response that we might get here. Oh, let's correct this word and spell it right. All right. In which column does A appear in the periodic table? So we're going to look at this element and we're going to try and see what's going on here. And this is a first 4 ionization energies. So this is going to be a case where we have to go ahead and see when our ionization energy increases the most. Okay, so we'll look at 1, and 1 increases is 576, so that's about 575. The second one is 1817, so it looks like it increases by about 1500. From 1817, it goes to 2745, so it increases by about 1200 or so. Or sorry, even less, only like 900. And then from this one to this one, it looks like it increases by a power of 5. Okay, so it increases by a power of 3 and then a power of 5. Okay, so that shows us that there's something that's going on here between the 3rd and 4th. Okay, and since there's something that's going on here between the 3rd and the 4th, that means that we can go ahead and easily indicate, hey, we're going down a couple of we're going down an energy level right about here, okay? Because this increases 5-fold between 3 and 4. We have a big increase. So we can go ahead and say that it is more than likely that it's going to fit in this column right here, okay? Because it's going to be the 3rd energy level that we get, okay? So we're going to say that it's going to end up being what's known as the 13th column of our periodic table, because it's 1, 2, 3, okay? And we know that it has 3 because the first 3, 1, 2, 3, are fairly easy to remove. So we're going to go ahead and put here 13th column. Okay. Now, B, it's asking what is the most likely oxidation number for element A? And it's saying how many electrons is it likely to lose? Now, in this case, we can use our same logic. Since it's a metal and it's in this 3rd column, and 3 electrons were able to be lost fairly easily, we would say that it's able to lose 3 electrons. So we're going to go ahead and say that its oxidation number is likely going to be 3 plus. Now I know I just said that we were going to lose 3 electrons, and the reason that it's going to be plus has to do with the fact that electrons are negative, okay? Question C right here is asking what's the minimum number of electrons that A must have. All right. And again, we could take a look at the periodic table here. We know that it's in this column, okay? And we see that boron is an atom, that it could be. Boron has 5 electrons. The only one that it could be with the least amount of electrons is boron. So we would go ahead and put 5 for this one right here. Okay? Because you have to be able to lose at least 3, and then it has to have 2 in that 1s subshell. Write the valence electron subshell configuration for this element. Okay. So, in this case, we should have a valence subshell of P one. Okay. And we know that it's going to be P1 because it's the first one in the P and it begins to lose those electrons. Can atoms of 2 different elements have the same valence shell arrangement? All right. So this next one is asking if it's possible to have elements that have the same valence shell arrangement if they're 2 different elements. And the answer is actually going to end up being yes for this one, okay? And the explanation for this one just has to do with the fact that it's an anion or a cation. So a good example here is oxygen, okay, because it's talking about anions. Oxygen can be 2 minus and fluorine can be 1 minus. This is a good example here. All right. Now, oxygen as a fairly, as an element, it has 8 electrons normally, okay? But this one here has 2 minus. So it would be 1s2, 2s2, okay? And we would normally have it be 2p4, okay? So this is oxygen's normal valence electron shell. And this is fluorine's. However, we just said that this was oxygen 2 minus, which means that it has an extra 2 electrons. And fluorine also has 1 extra electron. Therefore, we can say that these two do have the same electrons arrangement, same valence electron arrangement, and they are 2 different ions. Okay. Next one is 14, and it's saying that the first ionization for beryllium is 9.322 eV. The second one is 18.21 eV, and the third is 153. Okay. And it's wanting us to explain why the third ionization is so much higher. Okay. And in this case, we already know from the previous questions, like question 12, we already know, and we knew from before, that that has to do with a jump of energy level. So our explanation here is also going to involve us explaining that beryllium has 2 electrons in the second energy level. And those are easier to remove than the electrons in the first energy level. And the third energy, the third ionization, reflects an attempt to remove those electrons from the first energy level. Okay. All right. This is going to go ahead and close us out for the notes here. I hope that this is able to help you guys make some sense of it. Again, if you have any more questions, feel free to go ahead and ask me in class later. And I hope that you all have a wonderful rest of your weekend.